Hello, everybody. It's Carsten here with the third part of our Bind 9 series. This time, we talk about dnsdist and load balancing with dnsdist. And yeah, this is the part 3 of our Bind 9 webinar series. And we talk about installation and configuration of dnsdist, what it is, what we can do with this, like aggregation of metrics across a cluster of DNS servers, cache concentration, and do load balancing for authoritative and load balancing for resolver. And at the end of the webinar, after the question and answer section, we have a tutorial part that is completely optional, but that is for you there to get your hands dirty with dnsdist if you like to. So we have a couple of virtual machines. There should be one virtual machine for every participant. And we have prepared 3 tutorials that you can choose from, or if you like, you can even do all the 3 of them. And with that, you can experience dnsdist for yourself, installing that and do a little configuration. The 3 tutorials that we have is one for load balancing a group of caching resolvers. Second is load balancing a group of authoritative servers. And the third is to use dnsdist as a DNS over HTTP and DNS over TLS proxy in front of a regular DNS resolver. But we will talk more about that at the end of the webinar. So if you have a little bit more time, approximately 30 minutes after the webinar, please be invited to join us there in the hands-on tutorial part. So what is dnsdist? It's an open source DNS load balancer, and it's from the people who gave us the PowerDNS authoritative server and the PowerDNS resolver. While it is independent of the PowerDNS other DNS products, it shares some of the source code. It can work, or because it is independent, it can work with all standard compliance DNS servers out there. For example, with a Bind 9 server or with any other actually DNS server out there. So what can it do? So dnsdist receives DNS traffic and forwards the request to a downstream DNS resolver or an authoritative server or a group of them. And it can have different failover or load balancing policies. It has a response cache, so it can cache the responses coming from the real DNS servers or resolvers and give them out instead. So that can help us to build a cache for a whole cluster of machines. dnsdist can detect abuse and can, based on traffic patterns, do rate limiting or even block abusive sources. So if someone is launching a denial of service attack against a DNS server or is sending malicious queries, these can be detected by dnsdist and can be then dealt with, either blocked or being redirected. dnsdist has DNS over TLS and DNS over HTTPS support, and also DNS crypt. All 3 are transport encryption systems for DNS traffic. dnsdist can hook into the Linux kernel if it runs on a Linux operating system and can feed the eBPF virtual machine that is part of modern Linux kernels with rule sets. Basically, the eBPF is kind of a firewall inside the Linux kernel, and it can be used to block traffic directly on the interface between the network card and the Linux kernel. And the benefit of doing that there is that the packages are being filtered out and dropped at the first possible occasion in the stream when it comes into a Linux system. So instead of going through all the TCP/IP stack in the kernel and then hitting some DNS server in the user space, the DNS traffic, the malicious DNS traffic, is immediately blocked and thrown away, which is very CPU friendly compared to other stuff. dnsdist is configured and also operated by the Lua embedded programming language, which makes it very flexible. And we talk about that. It allows dynamic reconfiguration. So you don't need to stop and restart dnsdist to apply new configuration. You can directly go with an API into the system and make changes to the running configuration without any downtime. It has a remote HTTP API. We talk about that in this webinar, and there's a built-in web server that gives statistics and also serves as the API server. So let's see how we can install and configure dnsdist. So dnsdist is part of many Unix and Linux operating system repositories. We have the list here. Chances are that dnsdist is already in the repository of your operating system, and you can just use it right away by using your favorite package manager. But however, you should know that the distribution repositories might not have the latest release version available. So if you are looking for certain features, maybe some features that I show here in the webinar, they might not available in the slightly older versions that are in the repositories. If you need the latest and greatest of dnsdist, you can use the repositories that are provided by PowerDNS itself. They have repositories for Debian, Debian 9 and Debian 10, for the Raspberry Pi operating systems, for Ubuntu LTS, and for CentOS 7 and 8. And you can find them on the website repo.powerdns.com. And in the tutorial, we will show how to install them from these repositories. PowerDNS, which is part of the Open Exchange group of companies, offers also commercial support for dnsdist if you need to have that. And as a third option, you can install dnsdist from source. dnsdist is open source software, so you can download the source code and compile it yourself. It has a few dependencies, nothing really out of the ordinary. Please don't compile software on production DNS servers. That is harmful. You should, if you compile yourself, do that on a development machine, create a package, and then move the package over to your production machines and install it there. You can find detailed installing instructions on the dnsdist.org website. So what actually can we do with dnsdist? So one use case of dnsdist is to configure a failover system. dnsdist will then receive the DNS queries and distribute the queries among a pool of backend servers based on the availability of these backend servers. And if we want to have a failover system where only one backend system always receives all the queries, and only if that one major system is not available, then the dnsdist will send everything to a backup system. We use the policy first available. With that, we configure a list of backend servers that we want to use, and we give it an order, and dnsdist will then always stick to the first one in the order that is available. In the policy, in addition to the first available policy, we can also configure a queries per second limit per server. And if the configured query per second limit is being reached, then all the additional queries are sent to the next available server, which is one of the backup servers. So the failover does not only work if the major machine is down, it even works if the major machine, the main machine, is overloaded in terms of query per second. And this picture shows how such a failover system would work. The DNS clients will send the queries to dnsdist, And dnsdist then will use the first available, which is in this case resolver number 1, which is the active one. And resolver number 2 is idling around, just waiting for resolver 1 to having any problems. And if that would be the case, dnsdist will switch over to resolver 2. Now, how does dnsdist detect that resolver 1 is down? dnsdist sends DNS query every second to every configured backend server. And by default, that's a query for a.rootservice.net and the quad A record for that, so the IPv6 address of that. And if a response is coming back from the resolver, then that resolver is seen as being up and working. And if there's no response coming back, then that server is seen as being dead, and all the queries will be distributed to the other backend servers. Now, you can configure the query that is being sent, and we will show that in this webinar as well, how to do that. We can also do load balancing. And with load balancing, dnsdist will distribute the queries among all the backend servers at the same point of time. So all the backend servers are busy as long as they are up and are successfully get the health check. And for load balancing, we have several different load balancing policies. One, which is also the default, is the least outstanding one, meaning that dnsdist is recording how much DNS queries are still outstanding, not have where dnsdist has not seen the answer back from the backend server. And it will then send new queries to the one server that has the least outstanding queries open. Another policy is chashed, which stands for client hashed, and this will hash the query name and send all the queries with the same hash to the same backend server. That creates sticky queries. That means that queries with the same query name will always end up to the same backend server, and that helps with the caches because we don't need to have all the different query names and the results responses for them in the different caches, in the backend caches. Only a certain query will only go to one backend machine. And then we have the W hashed, and W hashed is also distributed based on the hashes of the query machine, meaning sticky queries, but there is also a weight configured to the backend servers, and the weight defines how many percentage of the queries are going to each backend server. So with chashed, the distribution is even. All the backend servers will get the same amount of queries, and with W hash, we can apply a weight to the backend server. So we can give one server, which is maybe a very powerful machine, like 50% of all the queries, and then we have 3 other machines that then get like 15% of all the remaining queries. We have a policy of W random. That is a random distribution, but again with a weight applied, so no hashing and no stickiness on the queries, just randomness, but with weight. And we have round robin, which distribute all the queries just around through all the backend servers without any hashing and without any intelligence, but very evenly distributed. If we don't like any of the built-in policies, we can augment dnsdist with the Lua embedded programming language and build our own load balancing policies. And here we have an example, which is actually a re-implementation of the round-robin scheme just in Lua. This is just an example how it would look like to create your own policy there. Because it's a full-blown programming language, you can have policies as complex and as specific as you would like them to be. But be careful, of course, having a scripted language, even though Lua is very fast, execute for every query that goes through the load balancer has some performance penalty. So be careful not to write too big applications there for the policy. So this is how load balancing would look like. The DNS clients send their queries to the dnsdist server, and dnsdist will then distribute, depending on the policy, to all the backend servers, which are resolver 1 and resolver 2 in this case. And the resolvers will resolve the names in the internet. DNSdist can also be used as a DOH, that is DNS over HTTPS, and DOT, that is DNS over TLS proxy and DDoS and malware protection. So basically, what we can use DNSdist for is to add new DNS features to an existing DNS resolver or to an existing authoritative server without a need to make any changes to the backend server. So we can add DDoS protection, we can add malware domain filtering or DNS over TLS and DNS over HTTPS capabilities to an existing already deployed setup without the need to make any changes to the backend servers, which is very, very nice. So here's an example about DOH-DOT termination. There is a DNS resolver that is not capable of DOH or DOT. Let's say that's a bind 911 machine that you can find in current Linux distributions. And DNS clients nowadays use DNS over UDP or TCP port 53 to talk to that DNS resolver, and that one talks to the internet. And now maybe the operator wants to enhance the offering with DNS over HTTPS and DNS over TLS. But we don't want to rip out the trusty and good running bind resolver. We just want to augment that. So we can have dnsdist in the same data center, maybe in the same rack somewhere. And that is offering DNS over TLS, DNS over HTTPS, terminates that, does all the TLS termination, and then forwards the query over classic UDP DNS or TCP DNS towards the DNS resolver, and that one does the normal resolution. And therefore, we don't need to make any changes to the existing DNS resolver, which is a very nice solution. We can use dnsdist to aggregate metrics across a cluster because dnsdist has a very nice way to export statistics and metrics. We can use dnsdist for that. So we have a cluster of multiple backend systems, and dnsdist will distribute the queries, and we can use dnsdist there to see all the statistics in a central and same configuration and statistics language. This is especially interesting if the backend servers are of different products. For example, if you cluster resolvers, and let's say you have multiple bind 9 resolvers and maybe some unbound resolvers, but you want to have statistics across all of them. Bind and unbound have different statistics channel, and it's not so easy to get the accumulated statistics out of them. You can do that with dnsdist quite easily. And this is how that would look like. The DNS clients will query dnsdist. dnsdist will distribute among the resolvers, and the admin will be able to query the metrics from the dnsdist system and see then overall statistics over all the cluster. We can use dnsdist for cache concentration. It's not a dnsdist is not a DNS resolver itself, so it cannot follow delegation and cannot resolve names. However, we can use dnsdist to cache the responses coming back from the real resolvers and send responses if the same query comes again. dnsdist can even be configured to serve stale DNS data. Stale DNS data means that the TTL has expired. This will work if there's no downstream server available. So in really catastrophic failure, let's say that the whole internet connection of a company is down, then dnsdist will still be able to give responses to systems, even though the outside world cannot be reached. Now, it's of course questionable whether that really helps if the internet is down, but in some certain situation it can help. And this is now how cache concentration looks like. We have dnsdist, and we have configured a big shared cache there, and it creates the cache across all the resolvers in the backend system. And we can use dnsdist for authoritative server resilience. We can have dnsdist as a load balancer in front of authoritative servers. And by using that, the dnsdist guards the authoritative servers against some malicious traffic. And we can just take offline any of the backend servers without impact on the service availability. If you do that without a load balancer in front of the authoritative server, still the built-in load distribution mechanism of DNS will take care of them, but some clients will see higher name resolution times because sometimes the DNS authoritative server that is taken down will be queried and there will be timeouts. So this is how dnsdist is usually used in an authoritative server scenario. We have here 3 secondaries and a hidden primary. The secondaries get the zone data from the hidden primary by zone transfer. And then the dnsdist is listed, or the 2 dnsdist machines are listed in the authoritative delegation NS records of the zone. So we don't have the authoritative servers in the NS records. Instead, we have the dnsdist machines and their IP addresses in the A and quad A records that are used for the NS records. And the queries go to the dnsdists, and they distribute to all the available backend servers. And with this, we can easily take offline one of the secondaries there, do a system update for a longer amount of time without any downtime of the service and any regression of the service, which is nice. So going deeper into configuration and deployment. So when you use dnsdist for high availability, it is important that you don't create a new single point of failure, which is then dnsdist. So you would like to make dnsdist highly available too. And you can do so either by having multiple dnsdist instances. And if dnsdist is working as a load balancer in front of resolvers, you would then distribute the IP addresses of dnsdist via your DHCP setup or via your IPv6 router advertisement setup. For authoritative traffic, we have already seen that. You can have multiple dnsdist instances in front of authoritative servers and then use the NS delegation records to point to the dnsdist instances. And a third option is to make the dnsdist instance high available through operating system means something like a heartbeat pacemaker on Linux or some other clustering solution that are available on other Unix systems or Windows systems. So configuring dnsdist. There's a main configuration file called dnsdist.conf, which is usually being found in etc dnsdist. And that configuration file is actually Lua source code that is read when dnsdist is starting and is then executed by the embedded Lua VM. So, which is nice is that the format of the configuration file is exactly the same format that you use for dynamic reconfiguration. Because if you do dynamic reconfiguration, you also execute Lua statements inside dnsdist to reconfigure dnsdist. And that's the very same Lua statements that you also use in the configuration files. And here we have an example dnsdist configuration file, and I'll walk you through that configuration file quickly. So in the beginning, we have everything that is starting with 2 dashes, at least 2 dashes is in Lua, it's a command. It's a little bit unusual at first because we are used to hashes or semicolons or something like that for comments. But in Lua, it's the dashes, but actually it's quite readable that way. So listen addresses and backend servers and policy and so on, these are just commands for the humans. Add local is the command to add a local listening address. And here we tell dnsdist on which IP addresses and on which port numbers it should listen on. And next, we configure the backend servers. That is, the servers that DNS requests coming in on the listen addresses should be forwarded to. And here we have 3 backend servers, one with an IPv4 address and 2 with IPv6 addresses, and with different query per second limits and an order that we use. Then we set the policy, which is weighted hashed in this case, and we define an access control list that defines which IP address blocks are allowed to send queries towards dnsdist. Next, we configure a cache, and here it's a cache for 10,000 entries, and the maximum time to live that we want to have in the cache is 1 day. If there are DNS records entering the cache with a higher TTL, the TTL will automatically limited to that 1 day. The minimum TTL that we want to have in the cache is 0. That is, we want everything that is not higher than 1 day in the cache. But of course, we could say everything like lower than 60 seconds is maybe too low, will never be asked from the cache. So we don't really do the work in putting that into the cache. If there is a temporary failure and we have to give an answer back, that will have a TTL of 60 seconds. And if we have to serve stale information, in case we can't reach any of the backend servers, that in this case, it's also 60 seconds. And the last parameter, the don't age, is actually a double negation. We can configure dnsdist to not count down the time to live in the cache. In this case, don't age false means we do actually count down the TTLs in the cache and expire the cache entries when the TTL is being expired. And then we assign the cache to the pool. The pool with the empty name is just the default pool. And because we haven't put the backend servers in any specific pool, they will be automatically in the default pool, which is the pool with the empty name. Then we configure the web server listening on an IP address and a port 8083 in this case, and we give it an access control list and a password. So anyone coming from the 192.0.2.10 address having the correct password will be able to access the web server. Then we have the console, which is used for the API and for dynamic reconfiguration with an API key. And API requests need to give that key in order to be able to use the API. And then we have some filter routes that block everything that will be resolved from any of the Facebook or DoubleClick domains, because for whatever reason, we don't want them. I already told you that we can do dynamic reconfiguration. And for that, dnsdist has a console application that we get if we start dnsdist with the parameter -c. And if we do that on a machine where dnsdist is already running in the background as a daemon, we will then connect to the running daemon and will be able to give commands on the CLI. And the CLI is actually a Lua REPL, that is a read eval process loop. Or print loop. So it will take Lua commands and will execute them and will print out the results. So in this case here, we have reconfigured the backend servers. The first command, show servers, gives us a list of all the current servers in the backends. And then the command new server with address 1111, which is the Cloudflare DNS, is being entered in the list. And then the next call to show servers gives us the new list, which now includes the Cloudflare server in the second position. And the web server can be configured. If we don't configure the web server in the configuration, it will not be active. So if you want the web server, you have to configure that. And you should configure that with a password and an access control list. Even though with the web server, you can't do really direct harm to dnsdist, it's advisable to not have that open to the internet. And this is how the web server looks like. If you go to the web server's page, it gives you a little graphical statistics on the working DNS dist, the number of queries per second and the server fails per second, and then the cache hit rate and the CPU utilization of the current running system, the IP addresses and the status and the latency of the backend servers, and the list of rules that you might have configured. So there's also the web API. The web API, of course, needs the web server to be enabled. And the web API currently can be used to query statistics in JSON format or in Prometheus format, which is a key value format, just text-based. And you can use that to read the current configuration from a dnsdist instance. In order to use the web API, the client, the web client, the HTTP client must present the API key that is also configured in the dnsdist configuration. And that needs to be sent with every API request. So now we should look at real-world configurations about consolidating the metrics. There are different options. The Graphite monitoring is a push option where Graphite is an open source Python-based monitoring application, and dnsdist can be configured to send the metrics to a Graphite server using the Graphite Naven Carbon protocol. And here we have an example in the configuration. So we send to the IP address 192.0.2.210, which needs to be a Graphite server running. Then we have some parameters that describe the data that is being received. So this is a push because dnsdist is pushing out the metrics actively to a machine. And we can also get metrics from the system with a pull setup. And that is what is being used for Prometheus. Prometheus is a popular monitoring solution that we talked already last webinar about, so I won't talk too much about that. And there is in the web API a URL endpoint /metrics, and Prometheus system can be configured to read that URL endpoint from the web API and read the metrics from there, and process that and send that to a Grafana server, or not send that to Grafana server, but use Grafana to visualize that. So here we have the cache concentration. dnsdist can have one or more caches, and we can have separate caches per pool. So we can have different backend servers in different pools and then configure different caches for the pools. That might be useful, for example, if you do filtering based on, for example, query names or locations, and you want to have different caches for different clients or different requests. Here's an example configuration. The first parameter is the size of the cache, the number of entries that can go into the cache. And I already told you the other options there when we talked about the full configuration. And once we have configured a cache, we assign the cache to a pool. So let's look how load balancing for authoritative server is configured. I told you already that dnsdist does the health check by sending a query for a root service.net a record towards the downstream server. I think I got it wrong in the beginning of the webinar when I talked about quad A records and IPv6. No, it's an A record, IPv4.
Correct.
Yeah, sorry about that. So, and if that health check query doesn't succeed, it then takes that backend server offline and will not query that again. And for an authoritative server, such a query might not succeed because an authoritative server usually only sends answers back for the own authoritative server. And yeah, most servers are not authoritative for the a root name service.net A record. So we need to configure a different health check. And in this configuration snippet that we see here, we do a SOA record query in the .in class, which is the internet class, for the name isc.org. And the IP addresses that we see here are the IPv4 addresses for the authoritative servers for isc.org. So this would be a configuration if we build dnsdist for clustering the authoritative servers for the domain ic.org. You need to take special care about SOA queries and zone transfer requests, because the SOA records might now being sent to the dnsdist instances. So secondaries that want to check for the SOA record and want to see whether there is a higher serial number on the primary server, they will send SOA queries, and the SOA queries will now end up with dnsdist. And if dnsdist is configured to load balance across multiple backend servers, the SOA query might end up with a different backend server than the following zone transfer request. And that might work, or it might fail. It might fail, for example, in the situation where one backend server has already been updated with the new zone content and another one hasn't. So because of that, it's important to send the SOA queries to the same backend machine than the zone transfer requests. And we can do that with a specific action that we see here in the code snippet. Here, we define a new backend server, which is of address 192.0.2123. And it has the name primary, and it's the primary server here, the one where all the management happens, or where all the changes happen. And that server is placed in two different pools. It's in the primary pool, and it's the only machine in the primary pool. And it's also a member of the other pool. And the other pool is the pool where all the other backend servers are also in there. And then we add an action rule, which is, or an action with an OR rule. So the OR rule says if the incoming query is either a SOA, or it's a request for a full zone transfer, or it's a request for an incremental zone transfer, then the pool action is primary, meaning that then the request should be sent to a machine in the pool primary, which is only the one machine, which is our primary authoritative server. And with that, we make sure that the SOA record and the zone transfer requests are always end up with the same machine. Now, the SOA queries and also the zone transfer requests are not coming from the secondaries machines anymore, but they come from DNSDist and the DNSDist IP addresses. So if you have access control lists on the backend service, you need to adjust these accordingly. In order to help that, you can configure in DNSDist which source IP addresses DNSDist should use to talk to the backend servers. So if you do access control list by IP addresses, you need to allow the IP addresses being used by DNSDist to send zone transfer requests. Of course, if you use TSIG keys instead of IP address access control lists, it's not a problem, because the TSIG signed or signature is part of the DNS request and will be just forwarded by DNSDist. It's very similar with dynamic updates. So dynamic updates, if you use them to maintain your authoritative DNS zones, these updates should be sent to the real primary authoritative servers and not toward the DNSDist load balancer. You want to send directly to the IP address or to the domain name of one of the primary authoritative server. That can either be done if you put the name of a real authoritative server, not the DNSDist instance, into the SOA records mname field, because that is being used by most dynamic update client software to figure out to which server a dynamic update should be sent. Or you can use the IP address or the distinct host name of a real primary server in the dynamic DNS client, for example, nsupdate, as we see it here with the server statement for nsupdate. And then we have notifies. Notifies happens every time a zone changes is being updated on an authoritative server. And if that happens, the authoritative server looks in the NS records of the zone and will send a notify to all the other machines that are in the NS record set. So it will identify its own name in there. It will not send a notify to itself, even though some older version of some DNS servers did that for some time, but not anymore. It will send notifies to all the other machines. And then the other machines will get information that there might be new zone content on the other authoritative servers, and they might ask for the SOA record and do a subsequently a zone transfer. Now, for notify to work, notify need also receive the real secondaries. And if the notifies being sent to a dnsdist instance, dnsdist will forward that to the backend server. This time also the backend servers must have an access control list that allow the notifies to be received from the dnsdist source address. As an alternative, you can configure the DNS servers with explicit notify, where you put the real IP addresses of the secondaries in there. So not the dnsdist instance addresses, but the real backend server addresses. So the notifies will not be sent to the NS record sets IP addresses, but the IP addresses being configured. Another alternative would be to use TSIG-based access control lists, because then you don't have any issues with IP addresses. dnsdist can do rate limiting, and you can filter DNS traffic or rate limit DNS traffic based on a couple of selectors. For example, you can select whether DNSSEC is in use or not. That is, if the DO flag is being set. Or you can filter by eDNS option, or you can filter by max queries per second per IP address or per subnet. So if a certain IP address or a certain subnet sending the queries is going over a query per second threshold, then the filtering or the rate limiting kicks in. There are other selectors like source network, opcodes, network class, query names. You can use regular expressions for the query names. Number of labels in the query name. For example, if you want to send all these long queries that some antivirus software is creating, or you want to block certain DNS tunneling software, you can do that by the number of labels in the query name, because they have a lot of labels in the query name sometimes. You can filter by return code, by the recursion desired flag. So you can treat authoritative queries differently from recursive queries, and so on and so forth. There are many, many more. So dnsdist is very flexible in this regard. And here's an example what you can do. You can even have dynamic rules in the system, meaning if certain thresholds are being met or certain conditions are being met, then a rule should get activated. And here we have certain examples rules. For example, the set rcode rate looks for a certain number of return codes. And this is the third line in the configuration snippet. It looks for NX domain responses if there are more than 20 NX domain responses in 10 seconds. So more than 2 NX domains per second, then we exceed the NX domain rate, and a filter is kicking in, an action is kicking in for 60 seconds. And after 60 seconds, this is being reset and evaluated again. And you can read about the dynamic rules in the linked URL here. So with these built-in rules and the dynamic rules, you can block quite a number of malicious traffic, or you can redirect that. Or on Linux, you can, even with the help of the embedded Berkeley packet filter, block certain DNS traffic before it enters the kernel, or before it enters the TCP stack of the kernel, and before it creates much load on the system. And you can read about the eBPF socket filtering on that linked URL here. So, and the last use case that we show here is the load balancing for the resolvers. Not the last one, the second last, or the yeah. So failover configuration. Here we have 3 backend servers, which are resolvers, and we set a server policy of first available, meaning the first one that is up and running will get the traffic. All the others are idle, as long as the query per second threshold of 1,000 queries per second is not reached. And we have a certain access control list and a packet cache configured. And here we have a configuration for real load balancing, not for failover. It's just change of the server policy. Instead of first available, we have here least outstanding, and the rest of the configuration is almost the same. Just as that with least outstanding, we don't need to configure a query per second limit. And I told you about the server pools. We can put the backend servers in pools. There's always a default pool with an empty name, and we can create any number of additional pools when we add a new backend server. So when we create a new backend server and specify a different pool, that automatically creates the pool if this is the first server in that pool. And then rules and actions can be used to select the pool for certain queries. For example, if you have a list of malware domains that indicate that a client is infected, but you can't block that client, but you want to isolate that client, you don't want the malicious traffic, the malicious DNS traffic of that client deteriorate the DNS service for all the other customers, you can then isolate these bad queries in a specific pool. And then all the clients that have this specific kind of malware infection, they will go to one pool with a certain set of servers, and they will just hurt themselves and yeah, all the groups of infected machines, but they won't hurt all the other clients that are just using the normal DNS resolvers. And this is the last configuration example. It's the DNS over HTTP and DNS over TLS termination, where we can use dnsdist as a proxy that terminates encrypted transport protocols and then sends the queries over classic DNS over UDP or TCP port 53 to the backend service, which, for example, could be a byte 9 server. And this, again, we've seen this graphic before, is how that works. Normal DNS clients just use the DNS resolver as always, sending over classic DNS, and the DOH or DOT client, which could be Windows 10 or could be Firefox or could be an Apple Macintosh system or an iPhone, they could then send the queries over DNS over TLS or DNS over HTTPS to the dnsdist system, which will securely terminate the encrypted traffic and sends in the data center network the query over to the real resolver, which then does the name resolution. So why such a proxy? Why not exchanging the DNS resolver with a product that can do DOH and DOT out of the box? Because it's a very easy deployment. You don't need to change the existing DNS resolver infrastructure. And you can scale through separate hardware server instances. So if you see that DOH and DOT traffic is increasing, you can just scale out by having multiple dnsdist instances without the need to change your DNS resolver setup. So, and that concludes the first part of our webinar. Here is the list of the upcoming webinars. We will have 2 more sessions about dynamic zones. Next session in May will be about the basics of dynamic zones and dynamic updates. And in June, we talk about the advanced topics of dynamic zones. And then we have the summer break, and we will come up with interesting new webinar topics for the second half of this year. And before we go into the tutorial session, let's see if we have questions, and maybe even some that I can answer, or someone else on the call can help with that.
So thank you very much, Carsten. We have a bunch of questions. Some of them have been answered or partly answered online. Some of them haven't. So I'm going to start with the ones that we haven't even attempted an answer first. So Philippe is asking, can you add or remove a virtual IP to dnsdist while it's running without restarting the daemon?
I haven't tested it. It should work. I don't see why it wouldn't, but I can't give an authoritative answer on that. I would have to test it. Maybe someone is on the call who, okay, cannot. Someone has tested that already.
Yeah, so Austin says he cannot. Okay. There's another question from Christian. What about query response logging, like DNS tap and EDNS client IP, client subnet identifier, range support? I think what he's asking is, can you do the query response logging in dnsdist?
I'm not sure about that. I would have to check that up. I'm not sure. I know about the response logging. I know that you can do EDNS clients IP range support. You can configure that.
Do you know what kind of actions dnsdist can do based on the subnet identifier? You mean block certain IPs? What sort of things can it do? Do you know?
Also not from top of my head. I would need to look in the reference, the configuration reference. That I know it supports EDNS client subnet. It can set that information, so it can, if it receives from a client, it can put that data into the DNS request and send it then to the backend servers. I'm not sure about the actions. I would have to read that up.
Okay, let's look at some of the other questions in here that have been answered or partly answered. So let's see. So Christian was commenting that Red Hat 8 doesn't have dnsdist or doesn't have the most current version. I think that's really probably just a comment. Someone asked whether or not the slides will be available for download. I'll post them soon as possible, certainly by Friday. I've put a link in the chat under the answered questions. There was a question from Christian about servstale. dnsdist does support servstale, and so he was, I think, suggesting that that's another use case, which is to enable servstale on the dnsdist as opposed to on the backend servers.
Yes, yes.
And then there was, finally, there's a question from Rick. Does the backend server see the IP address of the client so it can apply views, for example? And have you answered that one, that dnsdist can be configured to pass it on?
Yes.
I just lost the answer, but anyway, yes, dnsdist can pass the client IP on. So that's all the questions that I see. Let me just check the chat. Yeah, that's it for questions. So I think now I am going to pause the recording, and you can tell us how to get ready for the lab.
Yes.